1 part in about 100,000. The temperature from every direction of the sky of the cosmic microwave background is about the same to 1 part in 100,000, which is unusual. It requires very uniform initial conditions. Another thing that I mentioned was the flatness, and that's fine-tuned to about 1 part in 10 to the 15th. What happens when you invoke inflation? Well, there are different models of how this happens, but the basic picture is that it kicks in shortly after the Big Bang and operates in the first, 10 to the minus 37 to 10 to the minus 35 seconds of the universe's existence, in which it causes the initial space to expand by a factor of about 10 to the 60th and smooth everything out. Okay? That's the basic picture. But there's a huge amount of energy involved in that, and it has to shut off just right to get our universe. And so the shut-off energy of the inflaton field, as it's so called, has to be fine-tuned, depending on the model, to either as low as 1 part in 10 to the 53rd to as much as 1 part in, again, 10 to the 123rd. So essentially, you've filled a smaller hole by digging a much deeper one, is the basic picture. The other problem is kind of related to the idea of the fine-tuning. Well, it is related to the idea of the fine-tuning of the entropy, but parallel to the idea of, well, what if the universe were bouncing? Well, in this case, it's what if there was an inflationary period at the beginning of the universe? So you've got essentially a situation in which you've piggybacked one explosion on the back of the other. And the end of the first explosion, or at the end of the period of inflation, you've got initial conditions that are fine-tuned to 1 part in 10 to the 10 to the 123rd. So the fine-tuning of the inflation itself, which is an entropy increasing process, because it essentially is explaining things on the basis of thermalization, contributes exponentially to that, to the fine-tuning at the beginning. So you've got a hyper-exponential figure that's the end of a process that had to be also exponentially fine-tuned in order to end at that point. You see what I'm saying?
Yep.
So you've got an explosion that gives rise to another fine-tuned explosion. So the first explosion had to be hyper-exponentially fine-tuned. It makes the problem worse. So this is a problem for inflationary cosmology as an explanation of the fine-tuning of initial conditions. How are we going to go? But that doesn't do anything to explain the change, the laws and constants. How are we going to get the probabilistic resources to explain how the laws and constants of nature could be the way that they are and fine-tuned for life? Well, a resource for that was found in string theory. So what's string theory? Well, basically, string theory postulates that instead of particles, the fundamental constituents of nature are little filaments on the order of the Planck scale, which is about 10 to the minus 33rd centimeters in length, that can either be open or closed into loops, and they vibrate in different ways. And the way that they vibrate gives us the different particles that we observe. That's the basic picture of string theory. So what does that have to do with fine-tuning? Well, in order for string theory to work, it requires that space-time be 10-dimensional. 9 dimensions of space, 1 dimension of time. We only see 3 dimensions of space, right? So what happened to the other 6? Well, they're all curled up into little structures called orbifolds. And this is also on the Planck scale. But there are countless ways of what physicists would call compactifying those extra dimensions into those little curled up shapes. And the shape that those extra dimensions are curled up into influences the way that the laws operate in the macroscopic 3 dimensions. And the size of the different components of the compactification influences the strength of the coupling constants, the strength of the constants of nature. So here's a mechanism then whereby, okay, you've got all of these solutions of string theory. You can get different laws from different shapes of compactification. You can get different constants out of the sizes of the compactified features. So if all of these things could somehow come into existence, you'd have a way of varying the laws and constants of possible universes within the background laws of string theory in order to get a multiverse that had different components that, or different universes that had different laws and different constants. And if you had enough of those, maybe you could explain away the fine-tuning anthropically, because we wouldn't exist in those corners of the multiverse where the laws and the constants weren't compatible with our existence. That's the basic idea. It's called the string landscape hypothesis. Well, how are you going to get that to work? You need to somehow merge inflationary cosmology to take care of initial conditions and the string landscape hypothesis to get the different laws and constants. So the idea then is that you have these different compactifications, and they can transform from one to the other through the quantum decay of one of the features of the compactification that will lead to another universe of lower energy. So you start off somehow way up in the string landscape of energy, and then you cascade downward through the different compactifications of lower energy. And somewhere along the way, hopefully you get a universe that has the properties that ours has. Well, the assumption that you have to start in a really high state is a postulation, the only justification for it being that you need it in order to make the model work and do what you want it to do. Furthermore, think about the structure itself. I say bread-making machines, anyone. You're making a bunch of loaves of bread, right? And it's the product of a bread-making machine that's been programmed to do that. Well, here we've got a whole bunch of different universes that are being churned out of the mechanism of string theory. This mechanism is being invoked to explain the mechanical character by which universes can be generated, and you get one that looks designed over here. But what about the bread-making machine itself? It has laws that govern its behavior, otherwise it wouldn't work and it wouldn't produce loaves of bread, or in this case it wouldn't produce universes. So really all you've done is push the design problem up to the next level, and you can ask about the design of the bread-making machine itself, or in this case, the universe generator that's constituted by string theory or M theory and the landscape. What else? Well, there's another problem with the landscape in that it seems to suggest that we should observe low-energy supersymmetry. And we don't. In fact, they're hoping to find some evidence of it at very high energies at the new Large Hadron Collider in Europe that just got completed not too long ago. So we don't observe low-energy supersymmetry, and the landscape seems to predict that. So there's reason to have some skepticism there. And then you can ask, well, are there enough universes in the landscape to give us the right properties? And we don't know for sure. I mean, it seems likely you need versions of string theory that are compatible with a positive cosmological constant, and it looks like there are at least 10 to the 500 such models, which could potentially cover the fine-tuning if they all existed, and we had any reason to believe that they all existed, and we don't, really. But there are some other, well, first of all, so let's take stock of where we are. And I suggest, you know how in Alice in Wonderland they talked about believing 6 impossible things before breakfast. I suggest we have 6 credulous conjectures before breakfast here. There is such a thing as an inflaton field, which we don't know that for sure. It's a postulate. It was invented to solve a specific problem. It bears no intrinsic relation to any of the other fields that exist in physics. Secondly, there's a potentially infinite number of bubble universes. Thirdly, there are strings. Strings exist. Fourthly, our universe has 6 additional hidden spatial dimensions. 7 if you embrace M theory. Fifth, there's an infinite number of compactifications of these additional dimensions if you allow for a negative cosmological constant. And each of them potentially corresponds via inflation to an infinity of actual universes. And when you put all of that together, finally, you've got a situation that explains away the fine-tuning of initial conditions. Okay? Believe that? I've got some land in Florida I'd like to sell you. Okay, but What happens if you believe that? Well, it has some absurd consequences because you get a stupendously large space, much bigger than our universe, in fact, almost infinitely larger. What happens in such a context? Well, you get situations, physical situations, recurring. So somewhere out there in the multiverse, there's a clone of all of us, and we're sitting in a similar lecture theater, and I'm giving this talk. There's also another one where you're all sitting there and I'm standing on my head in the corner. It just, you know, you name it, let your imagination run wild, and somewhere in the multiverse, that's exactly what's happening. Parallel realities. You know, Mother Teresa is an axe murderer. There's also another problem that physicists are rather worried about. It's called the Boltzmann